Hello everybody, let us start our discussion today on special relativity. We will just continue from where we left last time, and particularly we will look at the mathematical object which you all call vectors in special relativity. Just to remind you, we call the special relativity the special relativity The special part comes from the fact that we deal with only inertial reference frames. On the other hand, when we will eventually learn general relativity, it can deal with any arbitrary reference frame or general reference frames. Remember that we start with the definition of inertial observers, where the relative velocity of any two observers always remains fixed with time. But in real life, that doesn't happen, and for that is the general relativity. Having said that, let us jump into introduction to four vectors in general relativity. Many of you have already heard and used these concepts, but there is no harm in revising them once because they come in a lot more difficult ways when you try to estimate things or try to do things in general relativity. So we'll revise them and go step by step, go a little slowly to start with. So we introduced these four objects earlier, and I will change the reference a little bit. We introduced this things called x alpha, which is components or the measurements along time direction x0, xyz direction 0, 1 and 2. X alpha gives you one event, or x alpha gives you one event when alpha goes from all 0, 1 and 2 and 3. So it's actually a set of four numbers. So this is a set of four numbers. Similarly, we also introduced the intervals between two events, and there the events were separated by infinitesimal distances in space and time, which we call delta x alpha. And remember that delta x alpha, let me write it here explicitly. This means that you have delta x0, which is c times the time difference, then this spatial difference in x, y and z, which are these three objects. We already know that this part, I can define a vector using that part, which I can call say delta x, and this delta x vector can be defined in terms of these three components. And as we said last time, that because we are talking about only the spatial part here, I can write it with a Roman index. But as we know that for the spatial vectors, their components can be different if you are considering different reference frames. So we have to write down a reference frame, to write down something here which tells me that which reference frame I am defining these components. So this is one good way of writing the vector delta x, which is essentially the displacement vector in 3 dimension, or I call the regular displacement vector. So in 3 dimensions, such displacement vectors are also sometimes denoted with an arrow, right? The arrow is from where you start the vector to where you end the vector. So in our old notations last time what we used, they goes from x1, x2, x3 to, sorry, xyz to x plus delta x, y plus delta y, and z plus delta z. So that is a 3 dimensional vector. A 4 vector I define the following way. You can see this is just borrowing the definition of vector from the 3 dimension. So I have delta x, which is the 4 vector. Because it's a 4 vector, to distinguish with a 3 vector, I write it with a bar under it. And again, it will have, given a reference frame S, it will have certain components, and that, as we said, we will write with the Greek indices. Okay, so just let me remind you, what are these different things? So this is the vector. This is telling you which reference frame. And these are the components of the vector in that reference frame. The fact that this is the components in that frame is important, because if I write the same vector in 2 different reference frames, the components will be different. For example, I can write this as in S reference frame, where I call these components as del x alpha. The same vector, and the same vector I can write in the S prime reference frame, where I may call the components as del x alpha prime, say. That prime denotes the fact that it's in a different reference frame. So the crack of the story is these are components of the same vectors. Different reference frame. For the word reference frame, sometimes I not use the word frame, sometimes I just use frame, but you understand usually, I think, what I am trying to say, so that's all right. So these are components at different reference frames. Now, as they have different components, it is obvious that the components will be different in different reference frames. So the question that comes is that how the components changes from one reference frame to the other. So how the components changes? You see, First of all, we realized that for the three-dimensional vectors that we knew of till now, we had three components, and the four-dimensional vectors has four components. The first type of transformation that one can think of are called translations. And it's very simple that I have the components, say delta x alpha, in one reference frame. This changes in the other reference frame to delta x say alpha prime. This will be equals to delta x alpha plus some vector which can be different. The components of that vector can be different in all four reference frames, but you see, for the 0, 1, 2 and 3, when alpha equals to 0, 1, 2 and 3, but these components are written in the reference frame, in the original reference frame, and when I add them I get the other one. So this is just basically what you are doing is you are changing your origin. So that's why this is called translation. So what are the other type of thing that one can do? Well, if you think of it geometrically, so let's say that we have only two axes, x and y, I can translate and I can rotate. So if I have x and y, set let me use of this place. If this is some region in my coordinate system, I can make it go somewhere else. So that's a translation. And this is 2D. The only other thing that I can do is I can make it rotate. So this may look like this after some time. So that's the rotation. See, for the rotation, you always require two axes because it happens in a plane. If I had only one axis, I could not have a translation. Could not have a rotation. So when I say rotation, so let me write down rotation here. So out of the four coordinates, I will always need at least two coordinates. Now these two coordinates can be both space coordinates. So I will get space rotation. And this is essentially the rotation that we have studied in classical mechanics. It is essentially the same rotation of the coordinates. You can get the Euler angles for this, for example. And we know that for rotation, I cannot just write something plus something as for the translation. Here I have to write a rotation matrix, and it will look like this, right? So this two things to point out here. One is that the indices that we are using, alpha, beta, etc., they goes up and down. For now, they are just to use the Einstein summation convention. Okay, so this is only for the time being, at least. So we'll try to understand what is I mean when I write an index upstairs and what I mean when I write an index downstairs. But the time being, they're just to use the Einstein summation convention, which means that because beta comes down here and up here in the same side of the equals to sign, there is a summation over beta sitting in front of this right hand side thing, which I am not writing, but I know that there it is sitting there. Okay, so that is first thing. The second thing is, this is a linear combination. this entire thing, what it does is that it gives me a linear combination of one coordinate x del one coordinate or the components in one reference frame in terms of the linear combination of the other. Okay. So delta x prime, delta x alpha prime is written as the linear combination of delta x beta, and the coefficients of that linear combination is coming from the rotation matrix. So the space-space rotations, what are the three space-space rotations possible? So remember that this you already have studied. So x, y, y, z and zx. So these are the three which are possible. Now, taking two coordinates at a time, I can also have space-time rotation, which is, I always take the time coordinate if I take it first. So it is like ctx, cty and ctz. How do I write that? Well, it will look exactly the same as for the space-space rotation. And let me do a little bit more things a little bit more correctly. So here only spatial coordinates are involved, which means that I should use only Roman indices. So this can be like, for example, xl, xl prime, and L here, M here, and M here. But here I should use the Greek indices because, as you see, that space and time both are involved. And that was my convention. And I write this matrix as, write this thing, so 4 by 4 things as the rotation matrix are 3-dimensional because L goes from 1, 2, and 3. But here I need a real 4-dimensional thing. So this is alpha prime beta delta x beta. And again, this is also, just like before, is linear combination. And this is what, this transformation is what you call the Lorenz transformation. So what is a Lorenz transformation? Two reference frames has a relative velocity and for this special case we consider only along x. So the relative velocity of the S prime frame with respect to the S prime I can write as beta times c times x cap. Okay. So in this case, what will be my Lorenz transformation? Now this quantities, there are 4 values of alpha prime and 4 values of beta prime, beta, which means that there are total 16 values which I can write in the form of a matrix, which is a nice way of writing these type of things. And this is, you should try and see that this indeed is giving the Lorenz transformation that you have all studied earlier. And the other thing I will like you to do is to figure out what should be the lambda alpha prime beta if I have arbitrary velocities along x, y, and z direction. What will be that? Okay, so this is the Lorenz transformation matrix, and let me still write here again that what I mean by this transformation. So delta x prime, x alpha prime is alpha prime beta delta x beta. And the linear combination is quite visibly seen here. This is about what type of vectors we are talking about here. Well, when we defined the vector for the vector for 3 vector, this is essentially a regular displacement vector, right? This vector we have been talking about is also a displacement vector, but in 4 dimension. So the delta x is a displacement vector in 4 dimension. I can also have a vector, if I can talk about a radius vector in 4D. How will I write it? Well, exactly the same way. I call this, say, x. I'm writing this in the reference frame S. It has 4 components x alpha. So a general vector, any general vector, also will have 4 components. If I call that general vector A, and I should write it in a reference frame, this is the reference frame we are talking about. This will have 4 components, A alpha, the set of these 4 components, define the vector in that reference frame. How the components will transform? So what will be the transformation rule? So from now on, all the transformations that we'll talk about will be mostly Lorenz transformations, because all the other transformations are either trivial or we have already studied. So how will this transform? This will transform. So when I say transform, the vector doesn't transform. The vector is always the same vector in whatever reference frame you look at. Reference frame is essentially your arbitrary construction. The vector is a physical quantity which exists in nature. So that is their same in for all the observers. So this is this. Just like the transformation rule here. So let's put this in a box. Also, let me keep something to remember here and something for you to think about also, is that the components of a general vector can have different values at different x. So what does it mean? It means that these components themselves can be function of the vector x. Let me call this beta. Okay, so keep this in mind. You must have studied this. One of these vectors can be the momentum vector, and you know for a particle that momentum can be different at different positions if it is moving in a force field. Now, as the vectors in 2D, these vectors also follow certain rules. Like, for example, if I have A plus b, this essentially means in the reference frame S, the components of this vector, which is a plus b, will be the addition of the components of the individual vectors. If I multiply mu, any scalar number, with the vector a, that if I write in that reference frame, it will multiply mu with each component of the vector a. And the associativity rule holds. I can go on a little bit, but as you can see, that what I am aiming at is that all the vector rules, vector addition, vector algebra rules, so to say, for 3 vectors also holds for these 4 vectors. There are differences which will come to shortly, but so far they are all mostly similar. Alright, so see, till now we have been discussing, we have been defining the vector in terms of its components in a given reference frame. But we are also familiar with writing the vector like ax x cap plus ay y cap plus az z cap, where x cap, y cap, z cap are the basis vectors or the unit vectors or the eigenvectors in a given reference frame, right? So let us now bring in the concept of the basis vectors. So what are basis vectors? In any reference frame, reference frame is same as coordinate system, as we have seen. There are some special vectors first thing to realize is that this is also not realized sometimes by when we read for the first time, when we deal with 3-dimensional basis vectors. Something to realize is that basis vectors are vectors, so each of them should have 4 components. So, and if I consider the reference frame again S, these components E0 I will call 1 at the position 0 and the rest out 0. E1. So these are not components themselves. So the basis vectors are vectors, and this vectors has 4 components. And ironically, 3 of them are 0. Now, the components of the basis vectors, so it may look like that though this vector is 1, 0, 0, 0, so if I write them in a different reference frame, the vector will still be 1, 0, 0, 0, but it doesn't mean that if I take a basis vector E0 and in another reference frame if I take the basis vector E0 prime, they are not same. This is important. It may look like that they are same because the components are same, but remember that the vectors are not just their components. Even in the previous case, when we talk about this type of transformation, if the components in the either sides are same, doesn't mean that the vector is same. Now, these 4 vectors can be written in a more simple way, expression in terms of their components. How can I write them? Well, what I notice is if I am writing the, say, the alpha unit vector, and if I want to write the beta component of the alpha unit vector, which we will also, this obviously is in a reference frame, and this shorthand I may write this as E alpha beta like this. This thing is 0 if alpha is not equals to beta. Like if I look at E0, if I look at the first component, 0 and 1 are different, then it is 0. It is only 1 when alpha is equals to beta, which means that this is equals to the Kronecker delta, where you know the definition of Kronecker delta, where alpha equals to beta, it is 1, otherwise it is 0. So I have these 16 components here, 4 for each unit vector, and there are 4 unit vectors, and those can be totally written in terms of the Kronecker delta, which is very nice that I can write this. And now that I have the unit vector, I can represent my vector, any vector A, in the reference frame S, as we are doing till now, like A alpha. Now I can also do the same thing as A alpha multiplied by the unit vector alpha. This is of the same reference frame. If I have it defined in another reference frame, then this will be A alpha prime. Okay, so one thing we realize is that this is a summation, right? So this essentially means A0, the 0th unit vector, plus A1, the first unit vector, A2, the second unit vector, A3, the third unit vector, right? And when I write it in a different reference frame, I just use another index. The index is summed over, so it doesn't matter what index I use. I use this just because it will be helpful for me later. Okay, so in a different reference frame where the unit vectors are also defined different, that's why I put a prime sign over there over B. Then the components will be different. And this is all we are familiar with in our 3-dimensional vector things. If we look at it a little carefully, now it looks like, so this I will put in blue because it looks like, this is a comment which I make in the back of my head, that the suffix, the down index, which we call the suffix, says which unit vector it is. I just put this here for you to think about it a little bit. I'm not making any serious comment on the prefix and on the suffix and the superscripts at this stage, up or down indices at this stage. Okay, the next question we ask is, well, we have learned how a vector transforms as you go from one inertial reference frame to the other. That is given by this expression. Now let us ask the question, how a unit vector transform? Does it transform the same way? Okay. So now we are asking this question, how does So we said that the unit vectors in one reference frame is not the same as the unit vector in other reference frame. So that is what we are trying to figure out. How does they transform? It may seem to us that okay, they are vectors, they should transfer the same way, but there is no harm to investigate it. To do this, let me start with the fact that A can be written in terms of unit vectors in this reference, and it can also be written in terms of unit vector in a primed frame. I'm just distinguishing the two frames, one with prime, the other without prime. And because I am now writing the unit vectors, I don't need to write that S and S prime anymore, because that information is already there in the unit vector. Now remember that A alpha prime transfers with the Lorenz transformation matrix in the following way. So why don't we use it here? So we can write this as A beta E beta equals A alpha prime is just lambda alpha beta A beta E alpha. And the right hand side I can rearrange a little bit. So this implies this. On the right hand side I can rearrange a little bit. I can see there is all these things are just summed over. I can interchange the things because there's no harm in doing that. So this is only one number when I fix alpha and beta. This is one number when I fix alpha and beta. This is also one number. This is not one number. This is a vector. But apart from that vector, lambda and A, I can always interchange with each other. So I bring A in the front, which means both of these terms has A in the front. So they write them in shorthand like this. So which essentially means that A is multiplied with both of them. A beta is multiplied with both the left and the right hand side. Now A betas are arbitrary, which means for this to be true, I should have E beta, which is a vector, that should be equals to lambda alpha beta E alpha prime. There is a difference between these two lines. The line in the top tells you how the component of a vector transforms. The line in the bottom tells you how the vector itself, one vector, which is a particular vector called unit vector transforms. Remember that E beta has 4 components, so as E alpha prime. Okay, so the 4 components of E beta are related to the 4 components of E alpha prime in this particular way. So this is a linear relation between numbers. This is a linear relation between vectors. So there is a difference, and that difference is manifested if you look at the transformation rules. For A, the primes are in the left hand side and the unprimes are in the right hand side. Differently, compared to the components of a vector. right? Now, let us ask the question, what is the inverse transformation? We have gone from one reference frame to the other, but we should be able to come back to the previous reference frame also. So what is the inverse transformation that will let us do that? Now, before the reason to ask this question, there is one more reason to ask this question. You see that the transformation rule that we have got for the components of a vector takes from beta, from unprimed frame to the primed frame, if you wish. On the other hand, the unit vector transformation rules we have got from the primed frame to the unprimed frame. So they are not the same direction of transformation. So one need to figure out both the forward and the backward transformation rules such that we can do both if we wish to. Okay, so how do I do that? To do this, first we realize that, as we have said earlier, these are 16 components, most of them are 0, but these depends only on the velocity between the two reference frames. And the velocity has 3 components, so it essentially depends on the 3 velocity components. And let me see where I have started doing the mistake. Yeah. See, this should be alpha prime. This should be alpha prime. Because otherwise you cannot sum over them, right? So this is alpha prime. What about the inverse transform? Inverse transform I should be able to write exact same type of matrix, but that matrix, because let us look at here, this is the alpha prime beta matrix we have. Because the inverse transformation will take me from prime to unprime, so in the right hand side I will have prime, which means the up index of lambda will not be primed. So let me call that mu, and bottom index now will be primed. What this will be a function of? Well, we know what it should be in terms of the previous one. If the transformation in the forward direction is with the positive velocity v, this should be with just minus v, because that is what we mean by the relative velocities. They just change sign if you see from either side. What is this telling you? This is telling you that if I write the transformation rule of the unit vectors here, like alpha prime beta e alpha prime, the inverse transformation rule, okay, so let me write the v explicitly here because that is something is important for this discussion, and then e alpha prime. The inverse transformation will be, just by the same token, we will write it as e equals lambda e. The only thing is that the right hand side coordinates will be now unprimed, so I call it mu. So I'll have a mu here and say eta here. and that eta will be primed. So this is exactly what I have here. And again, let me put in the velocity explicitly. This will be a function of minus v, and let me put back the e mu, and this is e eta prime, right? So these are the two transformation rules which are supposed to be. What we do not know is the relation between these two lambdas. What are the relation between these two lambda? This is what we do not know. So I put a question mark here. So let us try to figure it out. So what I do is I start from here and I write E beta as, fine, this is lambda alpha prime beta v. But now I can write E alpha prime from here. So what will E alpha prime be? Wherever I have eta prime, that I have to replace by alpha prime. So this will be mu alpha prime, and this is minus v, and then mu. Alright, and so these are vectors in either side. I can just look at one component, look at which component should we look at. So I should choose an index which is not present in the right hand side, otherwise I will have trouble. Look at the, say, eta component of this, and that will give me eta component of that. That was my shorthand notation. And remember, this was just, this we have argued is just the Kronecker delta. And what is that I have in the right hand side? The right hand side is alpha prime beta and the eta component of this will be again a Kronecker delta. So let me go through this again. Here I have a vector equation because both sides are multiplied by the unit vectors. Now I am trying to look at one of its component, which is the eta component. And if you look at the left hand side and the right hand side, the unit vectors E beta and E mu are written in the same coordinate system. And that is what we have achieved by writing this entire thing for E alpha prime. Once we have done that, I am taking the eta component of this vector and trying to compare them. If I compare, if all the components are same, they are written now in the same coordinate system, then the vector will be also same. So what I found is that in the left hand side I find this, and the right hand side I have this delta. So if I work out the right hand side, what do I get? Well, this Kronecker delta means that it is only 1 when eta equals to mu. And if I look at carefully, there is this alpha index repeated upside and downside, and there is this mu index repeated upstairs and downstairs. So there is summation over mu and summation over alpha prime. If I do the summation over mu, the term survives when only mu equals to eta, which means this I can write as this v. I can just exchange mu with eta, and that will be the right hand side. And the left hand side I write to the right hand side. So this is what you get. And this gives me the relation between the two lambdas. So for one lambda, you see the alpha prime is upstairs and the other lambda alpha prime is downstairs. So this gives me the relation between two lambdas, which is just the Kronecker delta. Okay, so we have studied some properties of the vectors. Let us now look at some vectors, some important vectors. So I introduce something called a space-time diagram for you. I believe that you have already come across this, and I consider only one spatial direction, which I call x. This is just for the representative purpose. It makes it quite easy to understand a lot of phenomena. Because of that, I am using the space-time diagram. So let me write both x is which is called x1, and ct t0 is the ct or x0 is the y-axis. Now in this, a particle is moving, and as we said, it will have different events. Its trajectory corresponds to collection of events, and these, so there, if I call these points, so there are different events in this trajectory, in its trajectory. Okay, and each of these events can be leveled by the vector x alpha seen from this reference frame. So this is all seen from the reference frame S. So this is essentially and that vector, if you want to really draw the vector, this I am drawing with dashed line because there are certain problem in drawing in this picture, but roughly this is the vector that you are talking about. So I'll just still put a question mark here so that you should not kill me just because of doing that drawing. What is more important is that along this line, we also said that the quantity tau changes, the measure of the time in the clock of the person or the particle who is moving in this zigzag line changes along this line. And in fact, we can parameterize our x with this thing called the proper time tau. So x is actually a function of the proper time tau. This we discussed in the last class also. But now we have a pictorial representation of it. So x alpha are the coordinates or the events along the trajectory of the particle measured from the reference frame S, and tau is measured in the reference frame of the particle himself, and the particle himself never changes its position with respect to it. So always its position coordinate is 0. It's not worth recording it, but you can always record the time coordinate, which is how much time has elapsed as he moves, as he sits down and we see him moving, and that is tau. So now I have x and I have tau. I can define one important 4 vector, the velocity 4 vector or the 4 velocity. Velocities are usually written with v, and so this is the v velocity 4 vector written in the reference frame x this is equals see, it has the dimension of the velocity. I have divided a vector by a scalar. The tau is a scalar. Tau, remember, doesn't change if you go to different reference frames. So this still remains a vector, and that is what I call the velocity for vector. Quick look at its component. So what is V0? V0 is d of ct by d tau, and that will take a c out, and dt by d tau, if you calculate, is gamma, and gamma is 1 by root over 1 minus v square by c square. I guess that you are already familiar with. If you calculate VL, which are the three spatial components, you will see that will nothing be x dot L, which is, I'm writing x dot L for the spatial velocities dx dt, dy dt, and dz dt, and times gamma. We also notice that there is an invariant quantity related with the four velocity. This invariant quantity I can construct by V alpha, V beta with a G alpha beta, just like we did for the interval. In fact, this is nothing but, if you look at this is nothing but G alpha beta. V alpha is dx alpha dx d tau, and this is dx beta d tau. So this is not far from the interval. It's just interval by d tau square. But what is this? So let's calculate what this is. Dx alpha, v. So the first term will be v0 square. V0 square is c square times gamma square. So let's take gamma square outside. Seems that it will come again. And for the real part, for the spatial part, I have vx square plus vy square plus vz square, which is my three velocities square, and times gamma. If I take c square also outside, you will see that that is what will remain. So this is quite an invariant. The invariant for velocity, invariant of the four velocity, is nothing but c square itself. Okay. Now it looks like I have defined, I have got two invariants by doing these operation with two different types of vectors. One is a position vector, one is a velocity vector. So is it very special? It is, because this is how we can define the dot products of the vectors. So let us do that. So what is a dot product of two vectors? If I have two vectors A and B, their dot product is defined in this way. And again, so I say definition, so I write definition here. If you ask me why, I will say it is a definition. Let me remind you, usually when I do a three vector dot product, it is ax bx plus ay by plus az bz. Here though, if I break it out, the first term is positive, so which is A0, B0, but from then on I have terms which are negative, unlike the 3 vector case. So let's explore certain interesting properties of this. If I have a 3 vector A, if I dot product it with itself, you can define the norm of the 3 vector, the length of the vector. I can do the same here. This will be just G alpha beta, A alpha, A beta. And again, I will write this explicitly because this is A0 square minus A1 square minus A2 square minus A3 square. As we will go along in this course, we'll stop writing things explicitly, but for the first few times, it is better to write such that we understand what is going on. What if I have the dot product of A plus B with itself? It will have this. It will have this. By the way, when I write it mod, that is how I define the norm. So the norm of the vector A is this. And then I will have 2 into now the way we defined a dot product was from the influence on us from 2 different products that we did, like G alpha beta, dx alpha, dx beta, and etc., where we found that they are invariant of the Lorenz transformations. This is constructed in such a way this is invariant of Lorenz transformation. So let's write LT. So now if you look at, this is a dot product, this is a norm of a vector which is A plus B. This is invariant. These are also norms, so they are also invariant. This implies that A dot B is invariant. This is like if you have 3 vectors, A dot B gives you the angle between these 2 vectors. So this is an angle in between 4 vectors. I don't know how to physically describe that, but that is something is interesting, that A dot B is also invariant. We call 2 vectors orthogonal if their dot product is 0, which means that I can write either A dot B or I can write as G alpha beta A alpha A beta equals 0. Sorry, this is not A, but this should be B, right? But you see that that is a coordinate dependent statement. So if two vectors are orthogonal in one reference frame, and when I say reference frame, I'm doing special relativity, I mean inertial reference frame. So they are so means they are also orthogonal in all others. Okay. Let's investigate some orthogonal vectors. So we have already seen this, that if I have 4 velocity dotted with 4 velocity, which is essentially G alpha beta, V alpha, V beta. This is an example. This is C square, which is invariant. This is a dot product, has to be. Now we know that. If I take a time derivative, when I say time, it is the proper time in both sides. Right hand side will be 0. C doesn't change whatever you do. G alpha beta are 1 minus 1 minus 1 minus 1 and 0, so they are all constants. I take the derivative of v with respect to tau. Now I define 4 velocities, so let us define 4 accelerations in this exact same way. So this is dv alpha, the time derivative is with respect to the proper time. So this is my definition of 4 accelerations. So I get w alpha, v beta, and the first term keeping constant, v alpha constant, and this derivative will give me w beta. But you see, g alpha beta is symmetric, so g beta alpha is same as g alpha beta. In the second term, I have both alpha and beta summed over, so I can I can interchange them, doesn't matter. Only thing is that if I change alphas to beta, I should change it in all places. So if I do that, I get g beta alpha, but as we said, it is symmetric, so that is same as g alpha beta, and then I'll get w alpha v beta, which is exactly the first term. So it is telling you that g alpha beta times w alpha v beta, which is nothing but the 4 acceleration dot product with the 4 velocity is 0. So 4 acceleration is orthogonal to 4 velocity. So that's one nice example of orthogonal vectors. One last thing we'll discuss today. We talked about scalar products or dot products. Dot products and scalar products are the same thing. They are interchangeably used. There will be a surprise for you now. So this is quite interesting. Dot or scalar product of the eigenvectors or of the basis vectors. What are these? Let's see. So if I have, let's take both as E0. So what is this? This is both E0s. The first component is 1 and the rest are 0. So once you square, you will get 1. What about E1 with E1? E1, the first component is 0. So let us do one of these. This is 0 square minus, this is 1. The second component is 1. And then 0 square minus 0 square. So this will be minus 1. And as you can imagine, E1 dot E1 or E2 dot E2 or E3 dot E3, all of these will be minus 1. What about the rest? Rest means, say, E alpha dot E beta, alpha not equals to beta. If I do this, you see, when I take, now this is not like the norm, which is dot product of two different vectors, but if they are different, alpha is not equals to beta means that they are two different eigenvectors. None of them has any common position where you have 1 or 1. So this is always be 0. How many components do I have here for these dot products between the basis vectors? You see, there are 4 basis vectors, and you can take dot product of each one of them with the other 4, with again 4 basis vectors. So there are 16 components. Interesting. And what are the components? So let us write this down. I can write this as E alpha dot with E beta. Well, all the off-diagonal components are 0. The diagonal components, well, E00 is 1. Off-diagonals are all 0. 1, 1 is minus 1. Well, this looks like this. Quite a familiar scene, you know. This is nothing but G alpha beta. So yes, that's it. This is G alpha beta, which we have been using so long to define dot product itself. We'll see the physical significance of that in a later class. We have learned a lot about vectors and their properties in case of special relativity, where the allowed transformation with velocity is the Lorenz transformation, space-time rotations or Lorenz transformation. We'll take it forward from here in the next class. Thank you.